Welcome to the deep dive, listeners. Today we're taking a look at something pretty interesting. It's Microsoft Research's 5.4 technical report. Have you had a chance to look at this one?
Oh yeah, I've been digging into it. This report's all about 5.4, a 14 billion parameter language model. But, it's not just about size with this one.
Right. It seems like they're really focusing on something different here.
Yeah, they are. The research team, they really prioritize creating super high quality data to train 5.4.
And that seems to be the key. I mean, just looking at the abstract and the introduction, it's clear. Data quality, that's their secret weapon.
Exactly. It's how they're getting these crazy results. 5.4 is performing incredibly well, even beating out way bigger models in certain areas.
Like those reasoning tasks. It's pretty remarkable. And right from the get-go, in the introduction, they lay out these three core pillars for how they build 5.4.
Yeah, let's talk about those. The first one is their use of synthetic data. And we're not talking about just any synthetic data. They carefully designed it.
To teach the model specific skills, like reasoning and problem solving. It's like they created a custom curriculum for this AI.
It's a really interesting approach, and this ties into their second pillar, which is all about curating real-world data. They've really focused on high-quality stuff.
I was noticing that in the introduction. Things like web content, books, code. It's like they're giving 5.4 a really refined diet of information.
Yeah, and then the third pillar, it's all about post-training refinement.
So fine-tuning the model.
Exactly. They use techniques like supervised fine-tuning, SFT, and direct preference optimization, DPO.
What does that actually mean? What are they doing?
Well, think of it as giving 5.4 feedback. They're shaping its responses, so the model learns to give you the kind of outputs that are actually helpful.
It's like polishing a rough diamond.
Yeah, that's a great analogy.
Now, in Section 1, they really emphasize that 5.4 isn't just copying its teacher model, which was GPT-4o.
Right.
They wanted 5.4 to be able to, reason and think on its own.
Yeah, and you can really see that in its performance on those STEM-focused Q&A benchmarks.
Oh, yeah, especially in things like math and science. It's really impressive. And it even beats GPT-4o in some of those areas.
It really highlights the impact of their focus on data quality.
No doubt. Okay, let's dig a bit deeper into their data approach, which they detail in Section 2. They have a whole section dedicated to it. It seems like they see synthetic data as more than just a stand-in for real-world data.
You're right. They see it as offering some distinct advantages. And in subsection 2.1, they explain how synthetic data helps with structured learning.
So instead of just throwing all this messy real-world data at the model, it's given a more organized learning experience.
Yeah, more like a tailored curriculum. And they even give the example of a math problem. If you were to write out a solution, you'd probably start with the answer.
And then explain the steps.
Right. But a language model learning from that would be super confused. They expect things to flow logically.
So the synthetic data solves that problem.
Yeah, they structure it in a way that makes more sense to the model.
Interesting. So it's all about presenting the information in a way that's optimal for AI learning.
Yeah. And in that same subsection, 2.1, they also talk about how synthetic data helps the model better prepare for real-world applications.
Because it mimics the kind of outputs that would be expected in those applications.
Right. It's like they're bridging the gap between the training environment and how the model will be used.
Now, this is where it gets really cool. In subsection 2.1, they lay out the 4 principles that guide their synthetic data creation.
Okay, let's break those down. So first up, we have diversity. They wanted to cover a really wide range of topics and skills.
Within each area where they wanted 5.4 to excel.
Yeah. So the synthetic data reflects that breadth. And then the second principle is nuance and complexity.
So it's not all just, simple, straightforward examples.
No, not at all. They wanted the data to reflect the real world, which can be pretty messy and unpredictable.
Makes sense. And of course, accuracy is crucial, as they say in subsection 2.1.
Absolutely. They didn't want to cut corners. Whether it's code that needs to run correctly or explanations that need to be factually sound, it all had to be accurate.
And the final principle is chain of thought reasoning. It's kind of like teaching the model to think step by step.
Exactly. And that leads to more coherent and well-reasoned outputs.
Okay, so those are the guiding principles, but how do they actually go about creating these synthetic data sets?
They get into that in subsection 2.2, and it's pretty impressive. They developed 50 different types.
Wow, that's a lot.
It is. And in total, about 400 billion tokens, each one with its own unique starting points and multi-stage prompting procedures. It's really
So
meticulous.
it's not like they just whipped these data sets up overnight. A lot of thought went into it.
Oh yeah, a ton of work. And one approach that really stands out is their instruction reversal technique.
Instruction reversal, what's that?
So for code generation, as they explain in subsection 2.2, they took existing code snippets and had another language model generate instructions for that code.
So it's like they're reversing the process, using code to teach 5.4 how to understand instructions.
Yeah, pretty clever, right? And then another key part, as mentioned in subsection 2.2, is validating the data.
Making sure it's all correct.
Exactly. For code, they run tests to make sure it actually works. For scientific data, they have specific ways to check for relevance, accuracy, and even difficulty level.
So like they built this whole quality control system into the data creation process.
That's a great way to put it.
Now, as good as this synthetic data is, they didn't completely ignore real-world data, right?
No, they didn't. In subsection 2.3, they discuss their process for curating high-quality web data and Q&A data. And it's interesting what they found about human-generated questions.
Well, God.
Well, they discovered that the organic questions that people ask, like in online forums or Q&A sites, were much more effective for training than anything synthetic.
Oh, wow. Yeah.
Yeah. It highlights the unique value of that real-world interaction.
I guess there's something special about the way humans frame questions and seek information that's hard to replicate synthetically.
Exactly.
And in that same subsection, 2.3, they talk about their search for high-quality web data. I mean, they didn't just scrape any random website.
Oh, no. They were very selective. They focused on sources like academic papers, educational forums, programming tutorials. They even had special pipelines to make sure they included content from the humanities.
Stuff like art, history, and culture.
Right. They wanted 5.4 to be well-rounded, not just a science and math whiz.
And they go into some detail in subsection 2.3 about filtering this massive amount of web data they collected. They talk about using classifiers trained on annotations from another language model.
It sounds complicated.
It is, but it allowed them to really pick out the high-quality content. And I was fascinated by their efforts to include non-STEM content. They even created a separate pipeline for that, which they describe in subsection 2.3.
Because they noticed that their filtering methods tended to favor STEM content.
Yeah. They wanted to make sure 5.4 had a balanced understanding of the world.
And they weren't just limited to English either.
That's right, they wanted 5.4 to be multilingual.
In subsection 2.3, they talk about gathering and processing documents in tons of different languages, and they use the same rigorous filtering techniques as they did for English.
They even used a language identification model called fast text.
Yeah, fast text. As they explain in subsection 2.3, it can classify text into 176 different languages. It shows their commitment to building a truly global language model.
Okay, now we get to section 3, the nitty-gritty of how they actually trained 5.4.
The heart of the process.
So they start by explaining that it's built on a decoder-only transformer architecture. 14 billion parameters, initial context length of 4096 tokens. They even extended the context length to 16,000 tokens later on during mid-training.
Right, it's based on a similar architecture to its predecessor, Phi-3 Medium.
But they made some key changes.
Yeah. In section 3, they talk about switching to the tick token tokenizer.
Why did they do that?
Well, tick token is apparently much better at handling multiple languages. They also went with a padded vocabulary size of 100,352 tokens.
Including a bunch of unused ones.
Right. And then instead of using a sliding window for attention like they did in Phi-3 Medium, Phi-4 uses full attention over the entire 4,000 token context length.
So they made some significant modifications to the architecture.
They did.
And then in section 3, they go on to describe the pre-training process. Phi-4 was trained on roughly 10 trillion tokens. They used specific schedules for the learning rate, linear warm-up and decay, a peak learning rate of 0.00003, a constant weight decay of a 20.1, and the global batch size of 5,760.
It's interesting how in section 3 they explain that they actually tuned these hyperparameters pretty carefully based on these shorter training runs.
Because shorter runs can give you a good idea of how things will go with longer ones, at least until you start to see overfitting.
Exactly. They also mentioned that they really thoroughly tested that learning rate warm-up stage
to make sure the training remains stable.
It was a really meticulous process.
Now, they also had a mid-training phase to extend the context length from 4,000 to 16,000 tokens.
Right.
We'll dig into that a bit later.
Yeah.
But first, let's talk about how they evaluated the model during pre-training.
Okay, so this is interesting. In section 3, they explain why they decided against using zero-shot evaluations. Because pre-trained models aren't usually very good at following instructions right away.
So they need some help.
Exactly. Instead, they opted for an internal benchmark that used a combination of log likelihood and few-shot prompts.
So they gave the model a few examples to help it understand what was expected.
Yeah, it's like providing a bit of guidance.
And in section 3, they break down these specific evaluations they use. They use log likelihood for MMLU, MMLU Pro, and ARCC.
And then they used a bunch of few-shot examples for tasks like Trivia QA, MBPP, Math, and GSM-8K.
It was a really comprehensive evaluation.
It was.
And in Table 2, they compare Phi-4's performance to its predecessor, Phi-3 Medium.
After pre-training.
Right, and the results are pretty impressive. Phi-4 shows significant improvements across tasks like MMLU, MMLU Pro, GSM-8K, and Human Eval.
It's a testament to their careful approach.
Okay, now let's jump into subsection 3.1, where they talk about their two-phase training strategy that they used for the Phi-3 models. And it sounds like their observations during this process led them to rethink the role of web data.
Yeah, they learned a lot from that experience. So in the Phi-3 models, most of the training tokens in phase 1 were from filtered web data. Then in phase 2, it was mostly synthetic data.
With a smaller amount of that super filtered, reasoning-heavy web data.
Exactly. But as they explain in subsection 3.1, they started to notice something as they developed their synthetic data sets. Adding more non-synthetic data wasn't really helping as much, especially for models the size of Phi-3.
So the synthetic data was getting that good.
Yeah, it was becoming so good that it was starting to rival, sometimes even surpass the value of the web data.
Fascinating.
Yeah. And they found that using more epochs on their synthetic data was more effective, especially for those reasoning-heavy benchmarks. And they even went so far as to train a 13 billion parameter model using only synthetic data.
Just to see what would happen.
Just to experiment.
It's like a scientific experiment.
Yeah.
But it didn't work perfectly, right?
Right. As they describe in subsection 3.1, those models trained solely on synthetic data didn't perform as well on benchmarks that required lots of factual knowledge.
Okay, so the models were good at reasoning, but they didn't have the breadth of knowledge that comes from web data.
Exactly. And they also noticed those models hallucinated more. They were making things up.
Which is not good. So it seems like a balanced approach is still the best.
That's what they concluded. Synthetic data is great for reasoning, but it can't fully replace the richness of organic web data.
Okay, so this brings us to their careful design of the data mixture they used for pre-training Phi-4.
Which is what we'll explore next. So subsection 3.2, this is where it gets into the specifics of that data mix they used for pre-training Phi-4. They really wanted to get it just right, find that sweet spot.
Like a recipe.
Yeah, a recipe for a powerful language model. They experimented with different combinations, trying to figure out the best blend. They looked at synthetic data, web rewrites, filtered web content, targeted acquisitions, things like academic papers and books, and code.
So many different ingredients.
They ran a bunch of ablations to figure out the best mix within a certain token budget. They mentioned this in subsection 3.2. They started with a shorter training run, 1 trillion tokens. This let them experiment a bit more efficiently.
It's like a test run before the main event.
Yeah, a pilot study for AI training. And they found that these shorter training runs usually give you a pretty good idea of how the longer runs are going to perform, at least until you start to see overfitting. They also noticed that 7 billion parameter and 14 billion parameter models perform pretty similarly, as long as the data mixtures were distinct enough.
So they could extrapolate from those smaller tests to the full Phi-4 model.
And Table 4 shows some of their findings from these ablations. They kept the amount of data from targeted acquisitions and code constant at 25%. And they played around with the proportion of synthetic data, filtered web data, and web rewrites.
Those made up the other 75%.
Right. And what they found is pretty interesting. A uniform allocation, so an even split between synthetic data, filtered web data, and web rewrites, it didn't perform that well.
Not as well as they expected.
No, which I guess makes sense given how impressed they were with the synthetic data. It highlights that, not all data is created equal when you're training a language model.
So did they try just using all synthetic data?
They did. They tested mixes with more synthetic data by itself and with web rewrites. And these mixes, they actually performed a bit better on most of the benchmarks compared to the final mix they ended up using for Phi-4.
So more synthetic data seemed to be the way to go.
Well, there was one exception, the Trivia QA benchmark, which focuses on knowledge. For that one, web data was definitely really helpful.
Okay, so even with all the hype around synthetic data, It seems like it can't completely replace web data for tasks that require a vast amount of general knowledge.
Right. And as described in subsection 3.2, they also found that the difference in performance between their final data mix and those mixes with more synthetic data, it basically vanished after the post-training stage.
So the post-training process was able to close the gap.
In a way, yeah. It suggests that the post-training can compensate for some of the downsides of using less web data during pre-training.
It's like they're fine-tuning the model to make up for any knowledge gaps.
Exactly. Okay, so now let's get into the actual final data mix for 5.4, which they detail in Table 5. They went with a 50-50 split between web data and web rewrites. That made up 30% of the total data. And the remaining 70%, it was mainly synthetic data, 40%, with the last 30% split between code data and targeted acquisitions.
So in the end, they did go for a more balanced approach, giving a lot of weight to both synthetic and real-world data.
Right. And if you look at the total number of unique tokens in each of these data clusters, filtered web data actually comes out on top, around 1.3 trillion tokens. Code comes in second with 820 billion, followed by targeted acquisitions at 580 billion tokens. And web rewrites and synthetic data had similar counts, around 290 billion tokens each.
That's interesting. Even though synthetic data makes up a larger portion of the overall mix, the biggest source of unique tokens is still that filtered web data.
Yeah, it highlights the diversity of the web as a data source. And they also mention how many epochs they use for each of these data sources.
How do they determine that?
Well, it was determined by the ratio of tokens allocated in the mix and the number of unique tokens in each source. So this ensured that, even those data sources with fewer unique tokens, they were still seen enough during training.
It makes sense. It's like making sure everyone gets a chance to speak up in a group discussion.
Yeah, good analogy.
Okay, so we've covered their data mix. Now let's talk about that mid-training phase, where they stretched 5.4's context length. Why was this important?
Well, subsection 3.3 gets into all of that. They knew that increasing the context window was crucial. It was key for tackling those more complex tasks, the ones that require the model to consider a lot of information at once.
So things like summarizing lengthy documents, understanding complicated code, or following complex reasoning that spans like multiple paragraphs.
Yeah, all of that. And during mid-training, they actually tested different data sources. They wanted to see what was most effective. They compared those naturally long context sources, like academic papers, books, and code, with data that they artificially lengthened by combining shorter samples.
So like taking smaller pieces of text and stitching them together.
Yeah, exactly. And as they explain in subsection 3.3, what they found was that the naturally long context data was much better for boosting the model's ability to handle those longer sequences.
It's like learning a language by immersing yourself in novels, not just memorizing random sentences.
Yeah, that's a great way to put it.
So based on that finding, what did they do?
Well, as described in subsection 3.3, they went even further. They filtered their non-synthetic data sets to select samples that were at least 8,000 tokens long, and then they prioritized those subsets that were 16,000 tokens or longer.
So they were really focusing on long context data during this phase.
Yeah, they were. And they also created some new synthetic data sets, ones that were specifically designed to meet this longer sequence requirement.
So they have this whole mix of long context data for mid-training.
Right. The final mix, as explained in subsection 3.3, was 30% this new long context data and 70% data from the pre-training stage.
So they didn't just ditch all the previous data.
Right. And to adapt the model to this longer context, they had to make some adjustments to the architecture. They increased the base frequency of rope position encoding to 250,000.
Rope position encoding, what is that?
Well, in subsection 3.3, they explain that it's a way of telling the model where each word is in a sequence, which is super important for these transformer models.
So it's like giving the model a sense of order.
Exactly. And ROPE, which stands for rotary position embeddings, is particularly good at handling long sequences. And by increasing the base frequency, they made those position encodings more sensitive to changes in position, especially over longer distances.
So the model could better understand the relationships between words that were farther apart in the text.
Yeah, that's the idea.
They also adjusted the learning rate during mid-training, right?
Yes. They lowered the maximum learning rate by a factor of 10 compared to pre-training. And they trained the model for 250 billion tokens.
That's a huge amount of data.
It is. And it really shows that fine-tuning a model on long context data, it requires a more, I guess you could say, delicate touch
Yeah.
to make sure it doesn't forget what it already learned.
It's like teaching an old dog new tricks, but with a super advanced AI.
Yeah.
Okay, so they pre-trained the model. They did this mid-training to expand the context length, and now they're finally ready to put 5.4 to the test. What benchmarks did they use?
Well, their benchmarking process, as described in Section 5, was really thorough. They used a range of standard academic benchmarks, specialized benchmarks, and they even created their own internal benchmark called FeeBench.
So they weren't just relying on those standard tests.
No, they wanted to really push the boundaries. The academic benchmarks included things like MMLU, GPQA, and math. Those are commonly used to measure a model's knowledge and reasoning abilities. And then they use specialized benchmarks for specific skills like coding, reasoning, instruction following, and handling long text.
They really wanted to see what 5.4 could do.
Yeah, they were testing its limits. And they didn't just compare it to models of a similar size. They also wanted to see how it stacked up against much larger models.
So they were aiming high.
Yeah, they were. And the results are pretty amazing.
I bet they are.
In Table 1, they show that 5.4 actually outperforms similar-sized models, like Quinn 2.5, which also has 14 billion parameters. And it even surpasses some much larger models, like Llama 3.3, which has 70 billion parameters, on certain tasks, of course.
It's incredible that a smaller model can outperform these giants.
It really shows how much their focus on data quality paid off.
It proves that bigger isn't always better.
Exactly. And they highlight a few areas where 5.4 really shines. In STEM Q&A, it performs exceptionally well. They mention in Section 6 that it even beats its teacher model, GPT-4o, on GPQA and math.
So the student surpasses the teacher.
In a way, yeah. And they also point out its impressive coding abilities. It actually outperforms even those larger llama models on the human evil benchmark.
So it's a math whiz and a coding champion.
But it's important to remember, no model is perfect. 5.4 does have its limitations. They mention in Section 6 that it can struggle with tasks that require really strict instruction following, especially when it comes to specific formatting.
Like if you tell it to format the output in a certain way, it might have trouble with that.
Right. And they also acknowledge that it sometimes hallucinates, meaning it makes things up.
So even with all that effort they put into the training data and all the fine-tuning, it's still prone to errors.
Well, keep in mind that these language models, they're still a relatively new technology.
Yeah.
And we're constantly learning more about how to train them and how to address these limitations.
It's like they're still in their adolescence, lots of potential, but still some growing pains.
Yeah, good analogy.
Now, they dedicate a big chunk of the report to safety and responsible AI. It seems like they're really trying to address the ethical concerns around these models.
Yeah, they start in Section 5 by pointing out some limitations with the usual benchmarks used to evaluate language models. They talk about data contamination, limited skill scope, biases in the benchmarks that use LLMs as judges, and the shortcomings of multiple choice questions.
So they're saying that the standard tests aren't always the best way to measure a model's true capabilities.
Right. They argue that many of the benchmark data sets are too similar to the data that's used to train the models.
Which can lead to those inflated performance scores.
Yeah, it's like giving a student a test on material they've already studied. It's not a true measure of their understanding.
And they also point out that most benchmarks tend to focus on a fairly limited set of skills.
Right. And they don't really capture the full range of what these modern language models can actually do.
And what about using other LLMs as judges?
Well, they're concerned that those evaluation methods tend to favor style and fluency over things like accuracy and reasoning, which can skew the results.
So it's not just about how well the model writes, it's about how well it thinks.
Exactly. And then there's the issue of those multiple choice benchmarks.
They might encourage models to just become good guessers, rather than really understanding the material.
Right. It's like teaching to the test.
So to address all of these limitations, they created their own internal benchmark, FeeBench.
And they outline their goals for FeeBench in Section 5. The first was originality. They wanted to make sure all the questions were completely new to the model.
So the model couldn't just rely on something it had already seen.
Yeah, it had to really think. Their second goal was skill diversity. They wanted to test different aspects of the model's abilities, so they included a really wide range of tasks in FeeBench.
Like what kind of tasks?
Well, for coding, they went beyond those basic tasks, like implementing a function. They included things like debugging, extending existing code, and explaining code. And for math, they went beyond just solving equations. They had tasks where the model had to find errors in proofs, come up with similar problems. It was really challenging.
It sounds like they wanted to make sure 5.4 could actually reason, not just regurgitate information.
Exactly. And the third goal, as explained in Section 5, was to develop really strict scoring methods, especially for those tasks where the model had to generate its own answers. They wanted to make the evaluation as objective as possible.
So they had to come up with ways to avoid that bias from those LLM judges.
Right. They created really detailed instructions and rubrics focusing on evaluating accuracy, logical structure, and making sure the model was following the task requirement.
So they were being super thorough.
They were.
And did they use FeedBench to guide the development of 5.4?
Oh, absolutely. As described in Section 5, they used it to make decisions about the data mix, to fine-tune those hyperparameters, and develop those post-training techniques. They even used it to pinpoint any weaknesses in the model and to get ideas for new data sources.
It's like they built this whole feedback system around FeedBench.
Yeah, it was a really powerful tool for them.
Maybe other research teams will start to adopt similar approaches in the future.
I think that would be really beneficial. Having those well-designed benchmarks is crucial for pushing this field forward.
Okay, so back to 5.4's performance on those standard benchmarks. Section 6 and Table 1. They provide a breakdown of how it did on a variety of tasks throughout the post-training process, and they compare it to both those similar-sized models and those much larger models. And as we mentioned before, it consistently outperforms its closest competitor, Qwen 2.5.
It does.
But they also point out in Section 6 that even though 5.4 scores a bit lower than Qwen 2.5 on benchmarks like Simple QA, DROP, and IFEVL, they actually believe that 5.4's behavior on Simple QA is better.
That's interesting. Why do they say that?
Well, they explain that the evaluation metric used for Simple QA, the F1 score, it isn't always the most informative when those accuracy levels are really low.
So the score doesn't tell the whole story.
Exactly. And they go on to explain that during post-training, they intentionally shifted the model's behavior to prioritize a good user experience, even if it meant a slightly lower benchmark score.
So they were more focused on making the model reliable and useful than just chasing high scores.
Exactly.
And that led to 5.4 refusing to answer those questions when it didn't know the answer, which, of course, reduces those hallucinations.
That's a good thing. It's better to have a model that admits it doesn't know something than one that makes things up.
Right. And they argue that this improved behavior, while not reflected in that F1 score, it actually creates a better experience for the user, which is ultimately what matters.
Absolutely.
And in Section 6, they also emphasize how well 5.4 performs on those STEM Q&A tasks, where it even beats GPT-4o on both GPQA and math. They say these results really highlight the effectiveness of their training methodology.
Which, as we've discussed, focused on high-quality data and reasoning abilities.
Yeah. And they also point out 5.4's impressive scores on coding benchmarks. But they do acknowledge that 5.4 isn't perfect, especially when it comes to following those really detailed instructions, particularly ones with specific formatting requirements.
Right. We talked about that earlier.
Yeah. And in Section 6, they attribute this partly to the fact that, their synthetic data sets, they were primarily designed for question answering and reasoning tasks, not specifically for instruction following. They believe that with more tailored synthetic data, that could improve 5.4's ability in that area.
So it's an area for future improvement. Okay, so we've covered their data approach, the training process, the benchmarks. Now let's shift gears and talk about that big section on safety and responsible AI. They get into it in Section 7. They talk about aligning the model with safety guidelines during post-training. They also talk about red teaming exercises and using automated testing and evaluations across multiple RAI harm categories.
They really wanted to ensure that 5.4 would be used ethically.
So they were thinking about the potential risks.
Absolutely. And they used a variety of techniques to make sure the model would behave in a safe and responsible manner. They used data sets that were specifically designed to promote helpful and harmless responses. And they used techniques like rejection sampling to filter out bad outputs.
It's like they're putting safeguards in place.
And then they used red teaming. They explain this in Section 7. They had this independent team, the Microsoft AI Red Team, and their job was to find any vulnerabilities in 5.4.
So they were basically trying to break it.
Yeah, to see if they could push it to do something harmful or unethical.
It's almost like an ethical hacking exercise, but for AI.
Yeah, that's a good way to think about it.
And how did 5.4 hold up?
Well, they had the AI Red Team spend 2 weeks testing it. in all sorts of different scenarios, trying to emulate average users as well as those who might intentionally try to misuse it. And what they found, as described in Section 7, was that while Phi-4's behavior was generally similar to the Phi-3 models, they did uncover a few risky behaviors.
So they were able to find some cracks.
Yeah, but those were addressed through additional safety post-training.
So they were constantly working to improve the model's safety.
They were.
And in Section 7, they also talk about testing Phi-4's resilience against those adversarial attacks.
Right. Those are attempts to trick the model into ignoring its safety training. They tried things like jailbreaks, prompt encoding, multi-turn attacks. It turns out Phi-4 was pretty tough to crack.
So they really put it through the ringer.
They did.
And on top of the red teaming, they conducted really thorough automated testing and evaluations across those different RAI harm categories, which they detail in Section 7 and Table 10. And these tests, they were designed to assess the model's likelihood of exhibiting harmful behavior in various contexts.
And they used a scoring system to measure the severity of any potential harm, so they had a way of quantifying the risks.
It's almost like they're grading the model on its ethics.
In a way, yeah. And in Section 7, they described the categories covered in these tests, which included things like child grooming, illegal persuasion, leaking sensitive information, promoting conspiracies, expressing prejudice, providing instructions for illegal activities, inciting violence. Really serious stuff.
So they were really trying to make sure Phi-4 wouldn't be used for any of those harmful purposes.
They were.
And what about the results? How did it perform?
Well, overall, Phi-4 performed really well on these safety benchmarks. It demonstrated that their efforts to develop it responsibly were paying off.
So they were able to create a model that was both powerful and ethical.
It seems so.
That's good to hear.
No, of course they're realistic. They acknowledged in Section 8 that Phi-4, like any language model, still has its limitations. One area where it sometimes struggles is in handling factual knowledge, especially when it's asked about specific people. They give the example of the model making up a biography when asked who is X, where X is a plausible name.
So it's not immune to making stuff up.
No model is. And as they explain in Section 8, this issue highlights that even with really careful training, language models can still make mistakes, especially when dealing with information that's not well represented in their training data.
It's like they haven't learned everything yet.
Exactly.
They also point out that Phi-4, while good at answering questions and reasoning, is not as good at rigorously following detailed instructions, particularly those that involve specific formatting.
Right, we've touched upon that. And they say this is partly because they focus more on those question answering and reasoning abilities during training, rather than strictly adhering to instructions.
So it's a trade-off they made. Considering their primary goal was to develop a model that excelled in those reasoning and knowledge-based tasks.
Right.
And then in Section 8, they also point out that Phi-4 can still make mistakes, even on reasoning tasks. They give an example where the model incorrectly states that 9.9 is smaller than 9.11.
So it's not a perfect logician.
Right. And they say that this example reminds us that even models that seem very good at reasoning can still be prone to errors, especially when dealing with concepts that require a deeper understanding of numbers.
Yeah, it's a good reminder that these models, while impressive, are still under development.
They also mention that because they trained it on so much chain-of-thought data, Phi-4 sometimes gives these really long, detailed answers, even for fairly simple problems.
Right, as described in Section 8. And they acknowledge that this might make those interactions with the model feel a bit drawn out, especially for users who prefer concise responses.
So it's not always the most efficient communicator.
Yeah, sometimes it gets a bit verbose. And they also mention in Section 8 that while Phi-4 can function as a chatbot, they didn't really focus on its conversational skills during fine-tuning. Their main goal was to make it good at answering those single-turn queries. So it's more of a question-answering expert than a smooth-talking conversationalist.
Makes sense.
Right. So it's important to keep in mind the strengths and limitations of any model and use it appropriately.
It's all about choosing the right tool for the job.
And then, wrapping up Section 8, they talk about those ongoing challenges in responsible AI development.
So they're not claiming to have solved all the problems.
Right. They recognize that even with all their efforts, there's still a possibility of biases creeping into the model. There's potential for it to generate inappropriate content, and there's always the risk of safety issues.
So they're being realistic about the limitations.
Yeah. And in Section 8, they emphasize that responsible AI development is an ongoing process. It's about continuous improvement and mitigation. They highlight the importance of really carefully choosing that training data, using those targeted post-training techniques, and getting feedback from those red teaming exercises.
So they're committed to making sure these models are used ethically and safely.
That's what it seems like. Okay, so we've talked about the data, training, and benchmarks. Now let's look at Appendix A.
Which goes into detail on their post-training data set and the process they use to refine the model's responses.
Exactly. And one of the things they really focused on was reducing hallucinations.
Which, as we discussed, is when the model makes something up instead of admitting that it doesn't know the answer.
Right. So how do you teach a language model to say, I don't know? That's a pretty interesting challenge.
Yeah, it seems counterintuitive. You're training a model to be knowledgeable, but also to recognize the limits of its knowledge.
Exactly. And they outline their approach in Appendix A.1, which is titled Refusal to Hallucinate. They start with a set of trivia questions, similar to the Trivia QA dataset, and they use 5.4 itself to assess its accuracy. They also bring in GPT-4o to generate a variety of responses to each question.
Oh, that's interesting. So they're using a different language model to help with the training.
Yeah, GPT-4o generates a correct answer, a refusal to answer, a question that's impossible to answer, and a refusal to answer the impossible question.
And so they're basically exposing 5.4 to different response styles.
Yeah, and then during the supervised fine-tuning stage, they use those question-answer pairs where 5.4 was usually accurate, and those question-refusal pairs where it was often wrong, and pairs with impossible questions and refusals to answer.
So they're guiding the model towards more appropriate responses.
Exactly. And then for DPO, they created pairs that reinforce the idea that, a correct answer is better than a refusal when 5.4 was sometimes right. And then when 5.4 was sometimes wrong, they reinforced that a refusal is better than an incorrect answer.
So they're training it to recognize its own strengths and weaknesses.
Right. And they specifically focused on those first 5 tokens of each response in the DPO data.
Why did they do that?
Well, they wanted to make sure the model was learning to start its answers in a way that aligned with these preferences. So it's not just about the final answer. It's about how the model approaches the question.
Okay, so they're teaching it to reason through the problem and respond in a thoughtful way.
Exactly. And then to track their progress, they use the simple QA benchmark, as they explain in Appendix A.1, which is mostly made up of obscure facts from Wikipedia.
So things that a smaller model like 5.4 wouldn't necessarily know.
Right, and they figured that made it a good test for their hallucination mitigation strategies.
Because if the model doesn't know the answer, it's more likely to make something up.
Exactly. And Figure 6 shows how 5.4's responses changed over the course of that post-training process.
It's interesting to see how they were able to shape its behavior.
It is. And in Appendix A.1, they point out that even though 5.4 doesn't get a super high score on simple QA based on that F1 score metric, they believe that its behavior is actually much better than the score suggests.
So the metric doesn't tell the whole story.
No, it doesn't. Because it turns out that the F1 score, which is often used for these classification tasks, it might not be the best way to measure performance when accuracy levels are really low.
So a model that just guesses randomly might end up with a higher F1 score, just by chance.
Yeah, that's the problem. And they explain in Appendix A.1 that by training 5.4 to refuse to answer those questions when it wasn't sure, they did see a decrease in the number of correct answers.
Because it was no longer guessing.
Exactly. But it also led to a dramatic reduction in the number of incorrect answers.
So it became more reliable.
Way more reliable. And ultimately, they argue that this is a much better experience for the user, even if it doesn't always result in a perfect score on a benchmark.
I think that's a really important point. It's not always about those raw scores. It's about how well the model performs in real-world scenarios.
Right.
Now, what about this judge-guided DPO that they mentioned in Appendix A.2? They use that for the second round of direct preference optimization.
Yeah, that's another interesting technique. So basically, they generate responses from GPT-4o, GPT-4t, and 5.4 for a given prompt. And then they use GPT-4o as a judge to decide which response is better.
So they're leveraging a more powerful language model to help guide 5.4's development.
Exactly. And in Appendix A.2, they actually provide the specific prompt that they use to guide GPT-4o's judgment. They instruct it to consider things like accuracy, style, and how detailed the responses are. And this helps them create DPO pairs that favor answers that are both accurate and well-written.
It's like they're training 5.4 to have good taste.
That's a good way to put it.
Okay, so we've covered some of the key post-training techniques. Now, what about this data decontamination process? They discuss it in Appendix B.
Right, data decontamination. It's really important for ensuring those benchmark results are reliable. And they point out that sometimes those benchmark data sets, they overlap with the data that's used to train the model.
Which can lead to those misleadingly high performance scores.
Exactly. It's like giving a student the answers to the test beforehand.
Not very fair.
Not at all. So they had to be really careful about this. And in Appendix B1, they explain how they tackled this problem. They created this really thorough decontamination process to identify and remove any text from their training data that was too similar to the benchmark data sets.
So they were basically scrubbing the data to make sure it was clean.
Exactly. And they describe the algorithm that they used, which uses those Enneagram matching and filtering techniques to find and remove those potential contaminants.
It's amazing how much effort goes into ensuring these results are accurate.
Yeah, it really highlights the importance of transparency and rigor in AI research. And in Appendix B1, they provide an example to illustrate this decontamination process. They show how they identified and removed a specific piece of text from their training data that actually matched a question in the AG Evil benchmark.
So they caught it before it could skew the results.
Exactly.
It's like they're playing detective, but with data.
That's a great way to put it.
Now, in Appendix C, they get into their evaluation process for those November 2024 AMC math competitions, which they use to test 5-4's mathematical reasoning abilities.
Right. They chose those competitions because the questions were released after they collected all their training data, so they knew it was a contamination-free evaluation.
So it was a truly fair test.
Yeah. And they explain in Appendix C how they formatted the questions, how they generated responses from the different models, and how they graded the results.
They wanted to make sure the evaluation was consistent and rigorous.
Absolutely. And they actually ran into a bit of a problem. They mention in Appendix C that the models often didn't follow that instruction to box their final answer, especially when they were providing a step-by-step solution.
So the models were giving the right answers, but they weren't presenting them in a specified format.
Exactly. So to get around this, they used GPT-4o to extract the final answer from each response. That way, they could grade the answer itself without penalizing the models for those formatting issues.
That's clever. It's like they're giving the models a bit of a break, recognizing that formatting isn't really the point of the test.
Right. And it also highlights how those small details can sometimes really affect benchmark results.
It's a good reminder that researchers need to be very aware of these nuances when they're evaluating these language models.
Now, Appendix D provides a really interesting glimpse into the different types of synthetic data that they created. They describe a whole range of methods, things like extracting and tagging excerpts from existing content, using those self-revision techniques, creating conversations from snippets, and generating those fill-in-the-middle exercises.
So they were really creative with their approach.
Oh, yeah, they were. And in Appendix D, they illustrate those techniques with specific examples. So, for instance, they show how they took a piece of scientific text and they annotated it with all sorts of metadata, information about the type of information, complexity, factual obscurity, whether it contained reasoning chains.
It's like they're creating a detailed map of the text.
Yeah, to help them figure out what parts were most valuable for creating those synthetic data sets.
And they also show an example of their self-revision workflow, which is described in Appendix D, where the model actually refines its own output to meet certain criteria.
It's like they're using the model to train itself.
It's a pretty cool concept. And they use this technique to create a really challenging reading comprehension exercise based on a scientific text.
Yeah, it's a really clever way to leverage the model's own abilities to create more challenging training data.
And Appendix D also includes an example of how they created a conversation from a factual snippet. They describe this multi-turn dialogue between two agents, showing how they use techniques like summarizing the previous context, introducing new scenarios, exploring different perspectives.
It's like they're teaching the model the art of conversation.
Giving it a crash course in social skills.
Exactly.
And then lastly, in Appendix D, they explain how they generated those fill-in-the-middle exercises. They take a piece of code, remove a key part, and then present that remaining code as the context, and that missing code becomes the correct answer. It's a really clever way to assess the model's understanding.
Yeah, it requires the model to actually think about the code
Right.
and figure out how different parts of the program fit together.
So it's not just about memorizing syntax. It's about really understanding the logic behind the code.
Exactly. And then they also talk about how they used AgentKit, which is this tool for building and training agents.
Okay.
They used it to generate data that helps 5-4 improve in areas like planning, reasoning, tool use, math, and error correction. They show 5-4 solving the Tower of Hanoi puzzle which is pretty cool. It highlights the model's ability to analyze a situation, think about its past actions, spot potential errors, and then, come up with a plan to reach the goal. It's like a mini AI
It's
strategist.
really impressive. It shows how these language models are becoming more than just, text generators. They're becoming problem solvers.
Yeah, exactly.
So overall, this report, the 5.4 technical report, it gives us a really detailed and fascinating look into the development of this impressive language model. Their emphasis on data quality, all the innovative training techniques that they used, and their dedication to developing this model responsibly. It's really remarkable what they've achieved, especially with a model that's relatively small compared to some of the others in the field.
And that focus on data quality, it really seems to be the key takeaway here. It suggests that, prioritizing that quality over just making the model bigger could be a really promising path forward for the future of language models.
It's really exciting to see where this research leads. There's so much potential here.
Yeah, there is.
Well, thank you so much for joining us on this deep dive into the world of 5.4. It's been a fascinating conversation.
It has. I always enjoy these deep dives. Until next time.